Hello and welcome to the video lecture series on contact mechanics in the course M7033T Scientific Computing with Applications in Tribology. My name is Andreas Almqvist and I work in the Division of Machine Elements here at Luleå University of Technology. So this is the first overview and motivational part of the fourth video lecture on the application of Fourier techniques and multi-level multi-integration in contact mechanics. So for this video lecture, or for this part of the course, I still recommend reading the course compendium for chapter 4 plus appendix A now. And if you want to dig in deeper into the sources, again, Contact Mechanics, the book by K.L. Johnson, and two papers, one by you and Faris, and another one by Stanley and Cotto. These two are recommended extra reading. They are, most of them are already integrated in the course compendium, but still it might be interesting for you to have a look at. Also, when it comes to optimization, minimization algorithms, I have one recommendation to you who like, and that's the book by Michael Heath, Scientific Computing, and there may be a newer edition than the second one out there. So this is the recommended literature for this course. The outline of the fourth video lecture on contact mechanics, which is about the application of Fourier techniques and multi-level multi-integration in contact mechanics, is quite extensive. So it has been divided into 6 parts, and the first part, which is this one, it gives an overview and motivation for applying Fourier techniques. The second part is where you learn about the continuous Fourier series and how to discretize this one, and how that can be very useful in various situations. Contact mechanics is one of them. Part 3, here we go through the discrete Fourier transformation and an application of this to numerically, very accurately determine the derivative of functions. Part 4 is where we move on from differentiation to integration, and we will look into continuous convolutions, which is a subpart of integral equations, and then we go into discrete convolutions, and we do both linear and circular convolutions, and that's because the elastic deflection in part 5, as we will see in part 5, can actually be represented as a circular convolution, and by means of this it allows for application of Fourier techniques to accelerate the computation. And finally, on the very last, the 6th part, I will give you a short introduction to multi-level multi-integration and how that can actually be done to accelerate the computation of the elastic deflection. So the recap then. Okay, we remember from before that we can solve the LCP problem by applying Lemke's algorithm, and in a finite number of pivots we can obtain the numerically exact solution to the LCP problem. We can also solve the associated variational principle-based problem, and the solution for this one, it will automatically satisfy the LCP, we saw that the variational principle-based problem was constructed in this way, with the total complementary potential energy V star, which actually discretizes into a quadratic function in P, and we minimize this total complementary potential energy with respect to P, is to take the gradient of V and find its zero. And when we do, we have minimized the energy, the total complementary potential energy, and we have the solution P. We can compute U, and yeah, we have solved the LCP. We have solved the contact mechanics problem. Slide. So I already more or less told you about what's on this one on the previous slide. But what's good with the variational principle-based problem is that it's a minimization formulation, which is there are frequently available methods for solving them. It's a quadratic form, it's rigorous mathematically back up here, and we have a guaranteed uniqueness in the solution. Okay, we also remember that the total complementary potential energy formulated this way may also be developed or extended to include the Boussinesq equation for the deformation, and here for a 3D half space. And in index notation it looked like this. And in matrix notation, well, the quadratic form is very clear. When we minimize, we actually find the values where U or Kp, which is U, which is the elastic deflection, minus G is 0. And that's exactly where we have contact between the surfaces. We can use the steepest descent method. It's a very simple algorithm to find the minimum in this case. And we saw a solution procedure, and it is all fine. It's an iterative solution procedure. It is iterated until we find that all points lie sufficiently close to a contact plane. And while doing those iterations, unfortunately, the elastic deflection must be computed many times, and that means, of course, a heavy computational burden. And the purpose of this part of the course, or this part of the contact mechanics series lectures, is to actually find a means to accelerate the computation of the elastic deflection. So here is the more concrete computational issue. So in 2D, you remember we had the auxiliary deformation, U prime defined as a matrix kernel times P. In 3D, it's actually the real deformation, which is K times P. If we perform the computation of the deformations in this way, we can clearly see that it will be an n squared number of operations in the 2D case, and in the 3D case it will be an n times m squared number of operations. So it's very heavy, because, for example, if you have 1000 nodes, which you easily need if you consider a rough topography. So if you have a surface measurement which represents your undeformed gap, then you easily need 1000 nodes in each direction to resolve this problem. Fine enough, and therefore you will have 10 to the power of 12 or an order of 10 to the power of 12 computations to carry out the calculation of the elastic deflection in the 3D case. So how can we use now something to reduce this burden? We will take a look at Fourier techniques. We will take a look also very quickly at something which is called multi-level multi-integration, which could also be used for this purpose. So when it comes to fast Fourier techniques, advantages with this one, I'd say it's that you can apply it to have high precision discrete differentiation. You can apply it to evaluate integral equations very fast and very efficiently, and it's actually a very straightforward and simple implementation, which if you have implemented it for the 2D case, it is easily expanded to a 3D formulation if you like.